So this is event tomorrow 125, Thursday, March 7th, 2024. So I'm calling it a revolution because tensor networks have been around for a while. And it's just, basically this year, kind of later last year too, is we're seeing actually good working models, better performance, more explainable. And that's always been a characteristic: efficiency, explainable, interpretability, but it's been accuracy, these types of things that have been matching that. So these are four of the outcomes or the goals that are wanted. So you can wind up with an MPS, which is one-dimensional, PEP states, tree tensor networks, 1D or 2D. So the big thing with this is basically there's a decent amount of literature. Now, I would call the first one a requirement, this Staudenmeier. And I think he's also involved with the Julia tensor network one. So I would definitely watch this. I've watched it at least twice, and it's very thorough as far as like you have to understand the basics of tensor networks. And it gets into the curse of dimensionality, which we'll discuss, singular value decomposition, which is really important, this TEBD algorithm for MPS. So MPS is a desired tensor network. It has the most favorable algorithms if you can get down to that one-dimensional MPS. And then the other two, the second one's, it's more commercial, but it's got some good updates as far as the types of hardware. There's many, it's not just CPUs and GPUs, there's TPUs. How to write, optimize, and customize tensor networks. And the last one, there was actually a demo tied to it, so I was able to work on the demo, and I'll be updating kind of the results that what they got, so I improved that. And the last thing is there's 5 2024 papers that I believe are definitely worth building off of. So the primary issue is just this, is you've heard it in quantum circuits. It's, in an ideal world, if we had a practical quantum computer in 10 years, you wouldn't have that issue. But in the classical world that we live in, and this is the practical solution, it's basically taking tensors, typically what they say is like over fifth order. So like this, specific one, so you reduce the problem down into a low rank structure. So the rank is the same thing as the bond dimension, and that's the lines connecting the nodes. So for instance, like this node or this index or this indice right here, S2 connected to S3, you want that to be as skinny as possible while still producing good accuracy. And that's the trick with this all. So an example of this is just regular 2D images. So you have an X and a Y coordinate, and now you have some value for color. So that's 3 dimensions. And for medical data, we can see that this is 4. So these typically aren't a problem on classical computers. But once you get up to higher and higher dimensions, it becomes an issue. So that's why tensor networks make some approximations in order to get get to these big data, big problem kind of solutions. So they call it, and this actually authored this Staudenmeier. So again, those kind of joining right now, I would say this is a requirement lecture if you're going to be designing or applying tensor networks in the future. You just have to watch this. And my overview is good, and I can pick out the big points, but I think it's an hour and a half long. Like I said, he's kind of gone on to design at least one of the other tensor network libraries, M. Staudenmeier. So all quantum circuits are tensor networks. Many tensor networks are quantum circuits. A tensor is a multi-dimensional array or generalization of a vector or matrix. So you see, scalar to vector to matrix. So one might say, scalars, we might use CPUs for vectors or like parallel processing with GPUs, and then matrices, especially higher order with a TPUs. In today's advanced GPUs, they have tensor processing cores to kind of supplement, to address, tensor networks or tensors. And so here's some of the kind of common tasks. So vector inner product. So V and W are actually, they have 2 legs and they're facing each other. Okay. So I'll show you that a little bit later. The trace, you'll see this notation here. And then contracting, say, for instance, an order 3 tensor with a vector to get some other solution. Okay. So, at this point, there's different algorithms that are used in tensor networks, and they have different degrees of expressive power for processing the same high dimensional problem. So here's the problem here. So it's 1, 2, 3, 4, 5, 6 dimensions. And it's one of those kind of like on the boundary, should you use a tensor network? The tensor network will always be faster, but again, you're typically losing some off of the, accuracy, or loss. And the 2024 papers have done a much greater job to incorporate tensor networks to get the most benefit out of them, because they were always thought to be efficient, and more explainable than neural networks, and probably more working alongside neural networks as opposed to replacing a lot of them. But I think there's some analogs between, tensor networks and convolutionals. So on the left is the matrix product state. And again, this is the most favorable. If you can get into MPS, which is one dimensional, go for it. If your accuracy is still good, if not, you have to do take less approximations to try to get to an appropriate or an acceptable, solution. Tree tensor networks you'll see too. So they're 1 or 2 dimensional, and PEPs as well. I think PEPs is just typically 2 dimensional. So this is the crux of it, and I'll give you a second to kind of like sink in here. So singular value decomposition, it takes an original matrix, we'll call it M, as in Mary, and then it breaks it into U, S, and V. Now U is an M by M orthogonal matrix, and it contains the left singular vectors of M. And S is the one that actually gets modified. So S is an M by N diagonal matrix. And this is the one that approximations are made off of, i.e. Some of these values get removed. Now V is another orthogonal matrix just like U, and it contains the right singular values of the original matrix. So you just see these things. So starting with the left here, US and VT combined back together this is U. So in tensor networks, you're not going to be able to, maintain pure unity. But I think this is where you would input, or it's going to contain part of a quantum circuit that you were wanting to run on a quantum computer. Now you run it on a classical computer. Now, as these terms, you see the 0.933, and this is just basic examples. This is what gets truncated down. And you see VT is the right side of singular vectors. So you see keeping fewer and fewer elements of S. So you'll see now just the 0.933 is there, and then all these other zeros. And this what makes it, more efficient to run than the original M matrix. And you see U and V did not change. So this creates a new matrix called M3. And it's using singular value decomposition to truncate for a control approximation for M. Okay, so M was the original matrix, and then this is our final one right here. And again, these are examples. So the thing to look at here, and I don't think every paper is going to faithfully show this, and just because people don't like changing the width of lines all the time, but that's how low rank is you approximate to a low rank matrix. So here's the same. This is singular value decomposition. M goes into USV. So you see these lines here on both sides of S got skinnier. And then the resultant here, this AB, is more efficient to run than M. Okay. So that's singular value decomposition. And you can see these types of approximations being made, as far as where to truncate values. And it's the same thing like neural networks make a lot of approximations to convolutional neural network. And I covered this in previous weeks. So it's a very common thing to make approximates in order to get to, these AI solutions that are significantly better or has more data than any human can do. Okay. Are there any questions at this point? And I see a couple people kind of joined on later, and also feel free to put in the chat with us. So, it's kind of the picked out field for quantum inspired that it's ready now. And it's, for, many different applications we're going to keep seeing. So the big thing with it is that it has, overturned, several quantum computing results. These are of the 53 qubit Sycamore. So this is the 2019 quantum advantage or quantum supremacy paper. And there's different, pros and cons. So quantum computers have noise, and then tensor networks have approximations. And these are all carried out in a noise-free, classical environment. And they call this one on the right a tie. So this is also an MPS tensor network. So again, getting everything down to, MPS is preferred if you can. And you'll see this green line here, this TEBD was the algorithm used to, you see that as the bond dimension could keep going higher, approximate levels for these other open and closed simulations. And I think those two are for the quantum computer. So those were for the 53 qubit. And I keep in mind, this lecture was also in 2022, because you can just get a different sense and vibe for tensor networks, that this is still an issue, and it's a mathematical conundrum. Like, you're designing tensor networks and you want them to be faster, or you want them to be higher accuracy, or these types of things. And a lot of times it'll be the only option moving forward, because it just has a significantly less number of problems, than other types of hardware technologies. So we see here, so in the green zone, tensor networks can always simulate shallow circuits or few qubits, and this can go, actually pretty high. I'll show you in a couple slides. And then as you increase entanglement and then, get more qubits or increasing width or depth, these are the types of things that it might not be able to. So for instance, if you're familiar with, a quantum gate, a single quantum gate, like a rotational Y gate, for instance, is you get an exact solution. But for controlled gates or 2 qubit gates, it's an approximate. And it's just, there's more math involved too. So, and again, this is 2022, but it's a good exercise. So this specific algorithm called TEBD, they say for the controlled application of 1 and 2 qubit gates, this 1 qubit gate is exact. Okay, so if you design quantum circuits and run them, on any device, that's what that's talking about, like a NOT gate, X gate, Y gate, rotational gate. But here's what and you've heard about tensor networks being, more limited in entanglement, and here's why. It's the math behind it, but you'll always incur some small error with a CNOT gate. So, the trick, or the emerging stuff in tensor networks, is trying to get the best solutions, which I'll show you in later papers, without experiencing a lot of, approximation error. It's not really truncation error, but if somebody says that, that's typically what that means. And then, so we'll see on the right here, in SVD, they say, but we can recover MPS form using truncated SVD in order to get it into MPS. This is the MPS tensor network here. So there's all these different, mathematical ways of going about, and the algorithms are really important themselves. So it's worth studying, because, the SVD, I've been covering TEBD, very commonly used algorithm. DMRG, you hear of those too. And so to get kind of like a wraps around this, is basically you have a specific quantum circuit and you're going left to right. So you're doing these, inner products across the circuit, and it's added over time, right? So classical hardware is amazing, it doesn't have any noise, these types of things. But the issue that you're dealing with is, as you go right, and especially with more and more 2 qubit gates, like CNOT gates, the fidelity starts to go down as you go across the depth of the circuit. So these are just basically crude diagrams to show you using TEBD. These are the types of issues that you can occur. And again, so for those just joining here, MPS is always preferred, but it has the best algorithms out of any other tensor network, but it's one-dimensional. And if you can get to MPS, you're probably going to have a very good answer. So again, don't get discouraged by all the approximations, because convolutional neural networks I just reviewed this, a couple weeks ago. It makes many approximations in order to get to a solution that humans would have a hard time doing. So here's an example. So it's the same kind of thing, quantum, it's 2 to the n. Now in layers here, they say holds even for thousands of qubits. I believe they mean qubits. I don't think they actually mean left to right. So it's 2 to the 10. They say this is still an easy simulation. I counted these. This is actually 21. It's just a pictogram of what's going on. But it's they say worst case for this specific algorithm, the bond dimension, this connect between the nodes, doubles every layer. So that is the hyperparameter, is chi, the bond dimension. Okay, so this is represented into an MPS tensor network on the right, and you want these chi's to be as small as possible for speed, but the smaller that you get, the less performance you typically get. So that's the issue. But again, this is 2022, and I don't think it's totally reflective of all the 2024 papers that we're seeing. But this kind of gives you an idea of what's going on as far as the choices to make. And this is an excellent illustration. So it's the inner product of two MPS tensors. So first you do these two, and then now you have this gray one, and now it's the gray one and the blue. And then now you have this bigger gray one. So it's that and the red. And it's the mathematics behind that. So the costs, in this case is x to the third. I don't know if this is considered quadratic, memory usage x squared. But anyways, this is typically these are simple problems. They're simple kind of like pictograms, but it's typically the most preferred to be an MPS if you can. Are there any questions at this point? And I saw a couple people kind of hop on, and we'll also do a wrap up at the end there too. So that was the basics. If you join late, it's the M. Staudenmeier. If you're doing tensor networks, I would say that this is a requirement. It's got too much information to pass by, and unless you went to school for this and did a bunch of book reports on it, I would definitely spend some time with that. So I'll have that in the chat too. Okay, so this next one, Tensor IR. So this is a company called OctoML, and one of these. So basically, what we'll start off is just this: is everybody knows about GPUs, but say for scalar computing, which I mentioned earlier, you're talking CPUs. Vector computing, you're talking vectors here, and tensor computing. And I'm still trying to, because on my Colab, I can run TPUs the same as CPUs, but it takes additional effort to do GPUs. And I can do a high RAM TPU as opposed to just a regular TPU. And typically it's an increase in performance with, an increase in rental time, which isn't bad. But anyways, it's not just Google. Many people think, oh, that was just Google's thing. It's NVIDIA. Inside their GPUs, actually, I think the primary number of cores are assigned to tensor cores. And AMD Matrix Core, Intel Matrix Engine, Apple Neural Engine, ARM, T-Head. So you see, it's a very prominent thing to do tensor network or tensor processing with TPUs. Now, in this specific case, it's more of an industry thing. So whereas the first lecture was more basics or fundamentals, this is, you are a tensor network programmer and how to write it, so you'd use this thing called TVM script. How to optimize is this interactive schedule on tensorized body. How to customize, decouple primitives. So they put all this together, and this is what they found to be the best solution at this time in 2022, is to manually write the code and do an automatic optimization to satisfy these three requirements of doing tensor networks. So, and here's some of the code here too. So these multi-dimensional buffer, loop nest, these loops are very common, blocks. So it's using TVM script, the first part, i.e. this is the manual code behind it. And then we see additional code here too, the bridge from the model to the hardware. So, there's a fair number, and I'll get to some of the other tensor network libraries too. This one in specific, the Stanford Quantum one, is Tensor Network, which is Google's, which is spelled like this, no space in between. And the gentleman that did it, his name is Chase Roberts. And it's another good, it ties the elementary into the future of a lot of the tensor network stuff. And one of them actually looks really good. And then, like I said, their demo is up. So I further modified that. Are there any questions at this point? So again, this is Google's, and Stanford Quantum did a discussion on this. So this is just very basic stuff. So remember I showed that earlier demo, two vectors facing each other, just looks like a node with a lot connected to another node. And say, for instance, this is the matrix here too, which is order 2. So an edge is an order. So this is an order 2, this is order 3 for tensor, and then this is scalar here. So just to go over some of the more basics. Now they called it dangling. I don't know if that's used as much, but the different types of edge types and trace. And I think where it connects with the code here is basically you have these two vectors and you're contracting. So I'll show you in the code coming up. connections and then contractions. So these are two vector, two vectors going into a scalar here. Now, the thing with diagrams and this type of stuff is I highly doubt all the literature accurately puts the correct. This big blob here is the bond dimension or the rank, and you want this to be as thin as possible. And as I showed you before in the other proofs, is basically in order to get there, you have to drop some of these singular values via singular value decomposition in order to get to this thinner line. So it has a lower rank. And if you've heard of the terms low rank approximation, this is what it's doing. I don't think SVD is the only algorithm, but it's one of them at least that does this. And this is a perfect illustration. So remember before I told you matrix M, and then it always goes into U, S, and V. Now U and V don't change, but S, in this case, the square root and drop the lowest to get to this smaller rank here. So again, when you're dealing with like many body problems, and they'll mention low rank approximation. I think a lot of times that's synonymous with tensor networks, and especially with the SVD algorithm on this specific slide here. So here's an example of some of the code, and I'll get to the stuff I did, but basically this is a matrix up here, a matrix B, and then the caret in this case is used to connect the two. Okay, so that's the connection. And then the @ sign is used to contract. So what's shown on this specific slide is the connection. Okay, so it's just we're looking at edge line right here. Okay, and this next slide is the contraction. Okay, so these two are contracted into C. And the whole goal of this, if you missed the first part, is basically the curse of dimensionality and having too many dimensions and it not running well on GPUs or DPUs. And these are approximative techniques, but so is all of neural networks, or at least CNNs and probably transformers too. So it's a very common thing to make approximations in order to be able to get to, using big data for big problems. So this one was the one I was kind of referencing here. This is transformers. So transformers is kind of like, some believe it's the replacement for convolutional neural networks. And then convolutional neural networks is also seeing some of the developments to try to catch up. So the big thing here is a tensor train. So this would be like an MPS on the feed forward of transformer. So that was the modification made to the code, is to insert this tensor network. So that drops the number of parameters by half, and it decreased inference time by half, keeping about the same perplexity. So there's usually something, the give and the take and all this stuff. But I think this is a good one. An average model now, this is 2022, an average model now might be 7 billion or 3 billion, with, chat GPT being up in the trillions. So we see this kind of, this was state of the art at the time. Now, the other example here is with fully connected layers. So if you have a neural network, you have all these, and in code, they just show up as dense, So you have all these nodes in one layer, and then next layer, you have nodes, that next layer of deep learning. Deep learning is typically over 3 layers versus just typical, neural networks. So deep learning neural net. So the algorithm behind that is this theta times WX plus B. And this is what dense or fully connected layer looks like mathematically, but using MPS or they call it tensor train decomposition. This is what the tensor networks looks like here. Okay, so it's just easier to process. And so this is the code, that they provided. And what was done here is I tried all these things. So this is the example of substituting a tensor network for one of the layers of fully connected layers. So what was done here is I tried to do all these different matrix combinations on the this TN layer, which is the tensor network, and that didn't work. And I tried standard deviation, modifications, nothing seemed to work. But I figured out what I had to change numerically. If I change these matrices, I have to change these 32s to, like, if I change 64s to 64s, and then below that, there's another line of code that's also 64s. So that did not work. So I kept this the same. Now here's where we see, and this jives with the previous slides in this specific, the Stanford quantum discussion, is basically, here's the connections, this A1 connected to X node, B1, A2 connected to B2. And this is what the tensor network, looks like. So they don't have to be huge, so I think this is actually a matrix product operator, if you're familiar with that. And at the C here, this is the contraction A at X node. That's contraction. Okay. So that's the code. Now here's the results. So we'll start up, and if you've run, in TensorFlow, you're familiar with these types of things. These are basically telling you what they are. So in the left here, we get this is 3 dense layers, meaning the first and the second are identical, and then the last one is the finish. I think this is for flattening. So in the first two, you'll see the first one actually has only 3,000 parameters, but the second one has, and these are trainable parameters like machine learning, the second one has over 1 million. Okay, so it's in the middle, so it has more connections between the other 2 dense layers. And you'll see total params is equal to total trainable params is equal to that. And for this, the results, so what you're looking at here is the dots stay the same, but you want everything to be a deep dark blue, and you want everything to be a deep dark a dark yellow that encompasses these dots. Okay, so in this specific case, you see that it's like a secondary blue and a secondary yellow or almost green, so not the greatest. So this next one, what was done, this is the author's model, and I had to install timers. And the big thing, if you go to compare data like this, you have to put seeds in because you'll get different results every time. So I put seeds in, their verbosity for the fully connect, this left one was set to 0. I had to change that to 2. So these minor kind of tweaks. So you see the number of parameters go way down. Now we're at like 10,000 or 9,000, something like that. And you see the results get much better. So you see the majority of the dots are in, this deep blue and the deep yellow. And the time is actually also faster too. So keep in mind, it's not as fast on a parameter basis, but overall it's faster, and the loss is much lower. So this one on the left, e to the -4, now we're at e to the -6. And what I did is, like I said, I experimented with a bunch of other stuff. I wasn't sure if this would work. And then I added 2 more tensor network layers here. So this put the parameters from 9,000 to about 19,000. And you can see it's just much better, as far as this primary blue color being more blue and less of the secondary blue color. And the way this is calculated is that there's known values of what these dots are, and it's the computer's predictions against that. So the time was a little bit higher than the other 2, and the loss was an order of magnitude better than just having a single tensor network layer, in this specific case. Are there any questions at this point? And again, feel free to put in the chat. Yeah, I mean, as far as the parameter reduction, because the circuit has been simplified, yes, I think that's the main thing is like, and if you have 3 dense layers or 3 fully connected layers in a row, like, they're deep learning layers, that middle one is going to see a lot of that. And I'm not sure, because what you're referring to, I believe, is this, these blue and the X there too, this for Alex. So yeah, a significant number of reduction in parameters, but there's some other thing that does make it run fast on a parameter basis. But they do a good job. So you see the lower rank here, so these lines between the nodes, they're thinner. So that's the main thing that helps it run faster, So I think that their results are really good, because the time was, 2 seconds faster, and then 2 orders of magnitude greater loss or lower loss. And then with mine, a little bit slower, but I add on an additional order of magnitude. So this is basically a 0.60 193 for this right one. And typically, if you have your settings, this is, you typically get 4 decimal points. So these are kind of, but this is what it looks like, so sometimes it's worth changing your decimal points to see what's really going on. So this paper here, so this is another 2024, and it says verifying quantum advantage experiments with multiple amplitude tensor network contraction. So I think that that's the the main thing with this, because the one it's comparing against is the 53 qubit Google Sycamore. And this has been done a number of times in a number of different ways with tensor networks to kind of, move past those results from 2019. So they say tensor network contraction algorithm systematically exploits classical advantage of current supercomputers, obviously in a much more practical way. And then the second one I've covered before, and this is the efficient tensor network simulation of the 127 qubit Eagle kicked icing experiment. So this quantum experiment that was run is more recent. It's on 127 qubit. And this is one of those, trying to dodge the quantum noise type of thing. And they thought they did, awesome job. But on the tensor network, they said they got significantly, and especially versus the quantum computer, significantly more accurate and precise results versus the 127 qubit circuit there. So that's the NYU and Flatiron. Now, this is another one. So, those first twos are kind of like versus other technologies. And then we're seeing this hybridness. So it's got a neural network and it's got a tensor network. This is by NSF funded, MIT and Harvard. So basically, this hybrid approach using, and it's called tensorizing, or you'll see in literature like tensorized, outperform both tensor networks and autoregressive neural networks on their own. Is that specific case? And then, so you see here, Multiverse, they just got funding. So they got, mostly due, I think, because of this paper, they just got $25 million. So this is Multiverse and some other international organizations. And it's all about compression. So they call this compact if AI. And the claim to fame is compressing Llama 2, 7 billion parameters, to 30% of its size, keeping 90% of the accuracy. And I think the kicker, because we're, traditional approaches like distillation, this is like compression just traditionally, or pruning, or quantization, which is like, limiting the decimal points on the weights, that kind of stuff, that it's controllable, it's more controllable and explainable than the neural network approach. So, these types of articles will probably go back and forth as far as just the accuracy or loss, or percent reduction in size, these types of things. But I think what's going on is the core, tensor networks are just known to be a lot more explainable, interpretable, transparent, however you want to look at it, than neural networks. And I think that's the advantage, so I've seen other kind of recent, just traditional compressions of LLMs. And I think the advantage will be, especially for medical and other sensitive data fields, is the explainability, interpretability of it. So this is another compression one too. I don't think the results were quite as good, and the models that they did it on were smaller, but it's Terra Quantum, and they do a lot of stuff in this space too. And they said they surpassed Distilled GPT-2 and KN GPT-2, and the code is publicly available. So it's one of those things that I think it's accessible through PyTorch, and it's open on the web to use this TQ compressor. And if I were to guess, maybe this is an introductory model, and then they're moving on to bigger stuff too. So here's the summary: is basically tensor networks utilize efficient algorithms to solve high dimensionality problems. So if you missed the first part, the curse of dimensionality plagues classical computing unless you make approximations, with approaches like tensor networks. And you saw the two algorithms, the SVD and the TEVD. So I went through the SVD, it's U, S, and V, and then you're always approximating that middle S matrix. And the level of approximations you make affects the time, if you want to go faster, or performance, if you want more accuracy. And TEBD is used for MPS. Now, the ones I didn't mention, that's on GitHub, TenPy, iTensor. One of these big papers, one of the fives, uses the iTensor. It's I think primarily in Julia. And then Quim seems to be decently big, Tensor Circuit. And there's other ones too. So it's the type of thing is like tensor networks have been around for a long time. It's just all of this, development of trying to get, understand circuits and develop quantum algorithms. Well, all of that's just going back into classical hardware. with dequantized algorithms and tensor networks. So many tensor network approaches exist to increase the efficiency of. So I showed you adding additional tensor networks in my code for higher performance. And it takes more and more effort to get to, lower and lower losses. And the tensor network significantly more accurate and precise versus the 127 qubit circuit. And then the hybrid approach using tensor network plus neural network outperform both tensor networks and these autoregressive neural networks. Okay, so we're seeing these different approaches in all this. Tensor network compressed LLM. This is the multiverse one to 30% of its time, over 90% of accuracy. And again, I think the pitch, is there's, and I'll get to a quote on the next slide too, is the inherent benefits of tensor networks. It's just inherently more explainable than neural networks, if you can do it that way, which seems to be the case. And this last one was the teraquantum. So compression surpassed distilled GP2. And this is the one that's openly available. So, you can search on, and I'll have these links up too. Now, this is another multiverse one. They said our tensor network approach naturally facilitates the extraction of feature-wise probabilities. This is key. Von Neumann entropy and mutual information, offering a compelling narrative for classification of anomalies and fostering an unprecedented level of, here we go, transparency. They say unprecedented levels of transparency and interpretability. And this has always been the issue, especially in sensitive data fields. People really want this. Something fundamental to understand the rationale behind artificial intelligence decision, which is probably more neural net is what that's talking about. So that was a 2023 by Multiverse. And that's the company to watch right now, I would say, with tensor networks, as far as I think it's all proprietary, but they're up there. And so there was a question here. So are there any trials on developing QGANs using tensor networks? I haven't looked into that. I know there's cases of comparisons between other GANs models and tensor networks. I've seen comparisons. So it's the type of thing like the two big things on, you probably know this, but like on Google Scholar, either search by 2024 or 2023 or search by date. So date will give you the most recent, which sometimes the quality is not good, but you get the latest papers. I would do searches for that. Any other questions?
Thanks.
Yeah, go ahead.
I was just saying thanks. I was wondering if QGANs, I've done a few experiments on hybrid QGAN, but fully complete QGAN. But yeah, if you're saying, maybe I should search the papers, recent papers.
Yeah, like I said, it's the type of thing, it'll take a little bit of research, and but it's a very active field, tensor networks, and I've seen comparisons to these other types of technologies.
Yeah, sure.
Any other questions?
I have a question. I noticed that NVIDIA CU Quantum supports tensor networks, and instead of seamlessly can decompose circuits into tensor networks. How good is that software technology when it comes to tensor networks?
Well, all of it's turning into more of a science, I think, at this point, as opposed to an art. And it's cuTensorNet is the one that works alongside cuQuantum, basically. And they've done a bunch of simulations to tens of thousands of qubits. And it's more like, it's not in a machine learning workflow. It's more like just calculate the amplitude like a quantum computer could. So yeah, I think that's the main things. I don't know the inner workings as far as, how exactly easy it is and kind of playing around with it. But I definitely check their website first, and I'm sure they've got a bunch of stuff. I haven't got a chance to go through it quite yet. And then obviously GitHub too.
I just ran one of the examples that simply takes the circuit, compiles as a tensor network, and executes and gives the results. So it looks like magic happens inside.
Yeah, and I don't know. I mean, like, it seems to me like with all this AI kind of doing your code for you kind of thing in 5 years, it seems to me that the ones that will succeed in these areas are the ones that know how the software works, meaning that you run it on your own, and now you're taking advantage of these types of things. But you know, if it's just doing it on your, it just depends. It just depends on what you're trying to do. But if that's an appropriate method for you, then you could use that.
Thanks, Kevin.
So, and for everybody else too, NVIDIA is definitely leading this charge as well. And the Coup Quantum stuff, but Coup TensorNet, Sandbox AQ, which is the Google spinoff, and they've gotten significant funding too. They, some of the more recent announcements have said, we're specifically using tensor networks. So that's kind of a thing to hang your hat on. So, it's the thing with like, so the other two wings of quantum inspired machine learning, I call it 2.0, is basically dequantized algorithms put a lot of quantum algorithms out of business, for future quantum computers. And then state vector algorithms, actually it was IBM and IonQ, they still did exact simulations, not using approximations like tensor networks up to 192 qubits, but that was for like 4 days with like what it would take to train a deep learning neural network just to run a single quantum circuit. So you're going to see, advancements in those too. But I think, and especially because what kicked up tensor networks so much, and again, was all of this quantum research that people really wanted to use on hardware, and it's just been delayed. And, with these 5 papers that I've showed you, it's basically, let's go with it. And, multiple people have figured it out, and they're using tensor networks to a more way they understand. Like if you're familiar with Hilbert space, like instead of using the whole Hilbert space, like on a quantum computer, you're using a small portion of it, but that small portion of it corresponds to high accuracy on classical hardware. So that's what multiverse has been doing. So, it's the understanding of it has finally kicked around, and I think the sky's the limit. There was a multiverse call for, it was, let's see, the Penny Lane one, so QHack, and one of the multiverse computing researchers got on and said, we have a whole team of people dedicated to tensor networks now, and this is reflectant with the recent publications. And then any other questions, anything regarded to the slides? Yeah, so there was another thing in the chat here. So this is basically, another simulator as well. And this might mimic kind of Jacob's thing too, is like, you don't know exactly what's going on. It just works. I think if you want to do like design the next awesome thing and stay ahead of the curve, like you kind of have to know what's going on at every step, as far as like this algorithm is doing this here. But I don't know, like if you're high throughput and that's what you need, as opposed to understanding everything at one point. So the simulator that was suggested is this Mimic by QPerfect, MIQ. And yeah, there's different approaches of going by this, but I think, and especially with all the news about, this auto coding kind of stuff in the next 5 years, is I believe that the expert coders now will be the ones leading applications of saying, I need this AI, in this computer, the supercomputer, to do this specific thing, as opposed to just designing like personal websites. I don't think it'll go as far as people are hoping, as far as replacing, many software developers. But, that's the thing, is you could be designing the next software that AI is going to be using. And now this tensorized, network is incorporated with convolutional neural networks. So it's a little hard to know, what's going on right now. And yeah, I would head over for the GPU resources to Colab. If you can get onto cloud or, Google Cloud, I would do that too. So they're just super cheap, like you can get the A100 for like $1.30 an hour on that specific one. And, say on Google Cloud, on one of these papers to simulate the 48 qubits neutral atom one. That was on like 112 virtual CPUs using like 224 gigs of RAM. The same thing for the 96 qubit. So, and that one's more like $4 an hour, just for comparisons. But like Terra Quantum does, and I've done in the past too, is run benchmarks, and if you can make them do it within a day, if you can show your data even better, like put it into a chart. But people have done that, and that'll save you so much time moving forward, because with all these penny lane demos that were mostly what I consider 1.0 code, meaning that it was meant for quantum computers, not for classical computers, is that there was just, many times the GPU would run slower, than the CPU, because there was some issue with like penny lane and PyTorch and the GPU, that combination of those three. So, at this stage, because Tensor Network's coming into swing, I would highly suggest that, whatever you're trying to do some benchmarks. And, QEDC has done these too, I think mostly for quantum computers, but not for like GPUs. So the other question, keep the questions coming for sure. Is there any recent quantum hardware that takes advantage of tensor networks? I don't think it's for that. Like the whole purpose of it is so you can get up to these higher dimensions on classical computers. And I just wrote a little blurb on this, and let's see here. There's basically like, 17 or 18 other obstacles that you're running into with quantum computers. So I asked that same question, actually, Jacob, to Qiskit and Pennylane this week, if they're going to make any more Tensor Network demos. And I think that's kind of opposing, their future belief of quantum computer. But I think at least there's one Pennylane TensorNet demo, just a very basic problem. The best one that I found is the one I presented on, and I'll have the code up. So that's the Tensor Network and Stanford Quantum, those dark background slides. That specific one is a really good place to start, because it's a specific thing. It's just saying like the slowest part, especially if you have like fully connected layers and one in the middle, million parameters, and not doing much for accuracy. So it's not always the case, more parameters, better performance. It's always going to decrease time, more parameters typically, if for a specific computing method. So, I would plan on using them, on classical hardware for a very long time. And the little blurb I did this week is basically that, like, and I compiled this over many months of research, is that it's for AI and machine learning. I don't see QML today having any impact with quantum computers. So, you could take a look at that. So for a variety of things, it's cost and availability, noise, decoherence, latency. You can't get the answer right away. It's many things. It's really not one thing. Many of the algorithms have been dequantized, meaning there's no exponential speed up. Tensor networks are doing a great job at running higher dimensional problems. And don't get me wrong, I think a lot of the credit, especially like the Seth Lloyds and the John Praskals and even Richard P. Feynman, before those two, they get the credit for dreaming up all this stuff. It's just that the intended purpose is going to be for it's going to be on, GPUs and TPUs. So, and we're seeing that in industry too, just people committing to this type of technology. So, for AI and ML, there's the time, with all this like auto code stuff, if the technology is not ready for like, with your current quantum solution, it's just going to pass the quantum stuff by. It'll get so ubiquitous and easy to use for so many people. So we're talking about, this, like the strength of innovation, just Kimmel 2.0, quantum inspired, can keep up with the AI, and AI will use tensor networks and potentially some of the other technologies. I don't know how much, for the other two. Yeah, and any other questions is fine. So yeah, there's a lot going on that I've seen. on the AI side, because this is a classical world. I know that goes against the quote, by Richard Feynman, but the future of humanity. I was just on a Toastmasters call, and people are just generating AI backgrounds like it's nothing. And it's going to continue like that. And their reliance to create websites. I don't know how much as far as like publishing papers or like the latest and the greatest. I think that will have to get incorporated by humans into AI. But if you're not familiar with what I'm talking about, it's NVIDIA and OpenAI. So NVIDIA, within this past couple of weeks, the CEO Jensen Huang, basically came on overseas, and he says that you shouldn't get a degree in computer science. So within 5 years, a lot of this is going to be auto coded by AI. So, I mean, from my perspective, because I had to learn all of this, and not only am I a much more efficient worker, doing code, is that was the only way that I really learned machine learning really, really well. And if you were to access, say, in like 3 years, OpenAI, and you couldn't check the model, you only just wanted a better solution, you're at a huge disadvantage, I think, because you have to tell, like, if you don't know what batch size is and learning rates and all these just very standard things in machine learning, then it's this saying has gone even from OpenAI, OpenAI or ChatGPT, NLP, this type of stuff, LLMs, they won't replace humans, but the people that use this software will have the upper edge, for sure. And I think that we're already seeing that, but to a more mainstream thing. So with everything, with quantum is I only see quantum inspired machine learning. And when I really got into this, there was a couple things. There was a QCware talk, and the gentleman had up like all the possible, quantum technologies that will be near term and current. And the only one that he had up as green was quantum inspired machine learning. And there's a demo, or I'm sorry, the survey. It's quantum inspired machine learning, a survey. And it's 50 pages. It's really well done. I think it's like 500 references. It's by Coyne et al. So I refer to this almost every week, and it really opens the doors, between tensor networks, which was what was discussed here, and dequantized algorithms. And then we're going to see improved state vector, which is exact simulation or close to it. We're going to see that too, but you're going to be cutting circuits depth with circuit partitioning or qubit reuse and mid-circuit measurement. So the authors, and that's where I got a lot of the stuff that I talk about, is from this paper. And it's all classical processing and classical data generating. Everything's classical, but it's the pace of innovation. There's no other like reason to seek other quantum technologies, because AI is going to be moving so fast, and we can use quantum inspired machine learning like today, tensor networks, So I think that's a thing to keep in mind, is the pace of innovation and how quickly, the world's going to be changing, in this next several years. And anything from robotics and agents, agents are basically software programs that can do tasks just like a human can. And deeplearning.ai put that up on their website, like and sign up for their batch. It's called the batch. It's like a weekly update. So they presented on agents this week. So, it's kind of like the heads up, if you don't know, and 3 years down the road, and then you're just assuming that you'll have the same type of job, I would start planning now, and I would take that experience that you have in coding, and now you're going to be doing more applications, but you're going to have a leg up because if the computer's messing up in a certain way or not doing something optimally. Like, it's just the human AI team is actually what FDA calls it. So yeah, so cuQuantum setup. So there's a couple things. I don't know where you're coming from, Alex, if you're using Penny Lane or... You go ahead, Alex.
Yeah, sorry for hiding.
Yeah.
No, I've used QQuantum before. We used it for Shor's algorithm, and then they had, I think, a new version of it. I had a lot of difficulty installing it. I'm just wondering if you have used it, if you're comfortable with it, if it's easier to use and install, or I think the mistake I was making was I was trying to install it on my own GPU over here, while they have those Docker
Yeah.
and things where they want you to, create an instance on their cloud. So I just wanted to get your feel for, what's been your experience with it. If you've used it.
I found a little shortcut. I put it in the chat here. It's basically if you use PennyLane, that was I set my Google Colab to whatever GPU, and then it was just a single line of code. And then also somewhere in the notebook, you might have to turn on, like that CUDA 0 kind of thing. You'll probably have to turn that on. But yeah, that was my way too, because I tried the same thing too with Dockers. And you could ask these things. Are you using PennyLane or?
No, I'm not using PennyLane.
Okay. Yeah. I'm trying to think the best way. And so you're saying you were on NVIDIA's website trying to do all this stuff?
I was on NVIDIA's website
Yeah.
looking at all the instructions to install it on my own GPUs. My device that has it has an NVIDIA GTX 4090 card.
Yeah.
So I wanted to make use of that.
I mean, just a heads up, so two things is I don't know as far as the industry with state vector simulation, it takes up a lot of RAM and time, but I found some hiccups myself, like I said, PennyLane, and then the NVIDIA GPU and PyTorch, but I could get it with NumPy. So I think there's an issue with PyTorch, but I don't know if it extends past PennyLane. So that's one of the things. The other thing I heard is another, member here said just do it with AWS. And I think that takes care of some things, but you're going to be paying a higher rate. So, but be wary because, some things are just notoriously slow. Like if you try to, do a neural network with a quantum circuit at 30 qubits, and it's a big circuit or it's a deep circuit, I think there's something in place where it doesn't like the PyTorch plus the GPU. So I haven't seen it work on. I know it doesn't work on Qiskit. So PyTorch and Qiskit and GPU I couldn't get to work either. So
okay, yeah. Jacob is saying that he installed it on his RTX 490.
Yeah. So I would ask Jacob. So but the more recent release installed without any issues. And I think it's all gotten better. So I remember at one point, it was only for the industrial GPUs and like the A100 and the V100, and the RTX is like a consumer. So yeah, so Jacob's saying the same thing too. He couldn't get Qiskit, PyTorch, and GPU.
Yeah, it was terrible. It's incredibly, it's slower than CPU, only much slower.
Yeah. So everything I've heard from my perspective, which has been mostly PennyLane, is to use NumPy if you're doing neural networks or those types of things. There's TenPy. I want to say TenPy for tensor networks is more similar to NumPy. I want to say, I don't know if anybody else has that experience or if it's under NumPy. I'm not quite sure, but many people. So the one that I saw that took it the furthest was the Julia. So this was the paper, I think it was the 127 qubit, the kicked icing experiment, versus the tensor network. And they said in specific, they could do these 6 or 7 things in Julia quite efficiently. So the one I included, I think it's L-tensor. So it'd be like L-tensor.j, or it's I-tensor, like capital I-tensor.jl. I think that one looks really good. But like just how we talked about this, a year or two ago, and it's like, everybody will be doing, well with tensor networks, I think.
Do you think that QAOA, without needing to, if you've got, a tensor network simulation and you can, get the landscape very easily with a state vector simulator, you don't really need a lot of parameterization. You don't need a lot of, running back and forth with classical. Would that actually become a little faster if you use?
With tensor networks?
Mhm.
Well, it's been done. Penny was it 127 qubits or 120 something? I think you can have different QAs. Anyways, Penny Lane did it with 127 qubits using circuit cutting on a supercomputer at NURSE, or it's basically Berkeley Lab. So they already did that. And there was one of these slides on the first one that I said is the requirement that you should definitely see that one. And I'll have these slides up too. And they said tensor networks are typically better for structured data. Even for some unstructured circuits, it will work as well. Like neural networks can only do unstructured data. Tensor networks better structured, these types of things. So they gave a specific example. My inkling, I would say probably, like if you saw the demos and you just go left to right and yeah, you could, it's something probably worth a Google Scholar search too,
Yeah, I'm seeing a lot of QAOA papers, and people are, I mean, I don't know why QAOA is suddenly more famous. But people are trying all kinds of different ways of, finding the parameters or doing a warm start or, and I mean, we know that the initial papers on QAOA, I mean, they were just, the examples were just on a simulator. So you didn't have to worry about the realities of a quantum computer or a noisy quantum computer. I mean, you can get the answer very quickly. So I'm saying if this is the way people are going, then I guess we don't have to worry about the real hardware. We just take an algorithm and run it on a simulator.
Well, the benchmark right now, just for state vector simulation is 192, but that took 4 days of runtime on CPUs and TPUs, like 5,000 of them that it would take for like training a deep learning neural network. So the 192, and that wasn't with any machine learning, it was just an amplitude. So then the next ones, in that paper, it's IBM, INQ, I included it, or I included in previous ones, IBM, INQ, 96 qubits, and that was on like a 224 gigs of CPU, So I would shoot after that, but they take CNOT gates and they would take this big cluster and condense it down to like one, and I think that was their trick. So for those that don't know, what I'm talking about is basically CNOT gates have been synonymous with not running well on simulators. And actually what they proved is that adding additional CNOT layers did not, significantly improve or increase runtime. So that paper is very interesting because it was to combat the neutral atom. If you guys are familiar with this 48 qubit in December of last year. And not only did they do it noise free on a simulator, they did it 100 times faster. And then they scaled it up again to 96 qubits and then to the 192. So 48 to, I think, 96 to 192. So what I'm saying is the 92 is probably in that range if you were using their techniques to start doing machine learning on, if you're doing state vector. If you're on the fence about something, it always comes down to dimensions on bigger problems. And then in that case, the state vector stuff, even with software techniques or circuit cutting, you're going to have to use tensor networks. I don't think there's any way around that. As far as like, should I use this or should I use that? It's always going to be, you're always going to have to do some type of approximations that, keep the majority of the accuracy.
Okay, thanks.
Any other questions?
I have a general question. What are you doing these days with the chemical Q device, and are you?
Yeah, so it took a couple months to get here, basically with dequantized tensor networks. So you've seen all the talks, and that was my first tensor network up and running. And now everything seems like, okay, this goes here, because obviously in medical, these are explainability, transparency. These are very sought after terms. So I see that being a fit. And tensor network development across the board, just, everybody should be doing it, and especially for medical. And we'll see what dequantized algorithms is, mostly to put the QML quantum computers kind of on hold. And, state vector algorithms. We'll see, because if there's some advantages of running, pure state vector algorithms at 90 something qubits, or there could be some applications there too. But it's definitely going to be more in tensor networks, and that's what I'm planning to do the next couple of weeks is code, with tensor networks.
All right, good.
Just a quick comment on installing on Quantum. There is a problem, always a problem with NVIDIA, that there's a slight discrepancy between the software like Quantum and GPU drivers. So I need to be very careful which driver you pick, or else, like it in my case, destroyed my Linux. I had to recover my whole Linux setup.
Yeah, so I don't, because if you can run things on TPUs, like I said, in most, if not all of the notebooks I was paying attention that I could run TPU, I don't have to do any of that stuff. So say, for instance, the 192 qubit circuit by IBM Quantum and IonQ, they use CPUs and TPUs in Google Cloud, right? So if you have a notebook that you're having those issues, that's an option too, is go through Google Cloud. And it seems like pretty significant hardware for not that much more than Colab, A100, what is that? 40 gigs is like $130 an hour. So your step up, I checked, was like to like 224 gigs, just CPUs. Anyways, don't rule out the CPUs either. But as far as optimizing stuff and getting things to run absolutely the best you can, sometimes it's with TPUs. It's actually, the GPUs have mostly TPU cores. And that's the number one, if I recall correctly. They have other ones too. But anyways, that was their explanation for this really challenging Clifford circuit part of the, the Harvard Q era 48 qubit, is it had to be run on a TPU in order for that to be processed in any due time. So I would definitely research the TPUs as well. Awesome. Any other questions? Appreciate everybody coming on. And let's see here. So yeah, this is event seminar 125, Thursday, March 7th, 2024 for Tensor Network Developer Revolution. My name is Kevin Kocek. I appreciate everybody coming on. Have a good rest of the night and have a productive rest of the week, everybody. Take care.
Thanks, Kevin.